Hello friends, welcome to the second part of chapter number 1 of class 12. In the first part, we have discussed the concentration terms in which we talked about molality, mole fraction, mass percentage and the relation between them and some questions or numericals based on those concentration terms along with previous year questions. So in the second part today, we will discuss Henry law and Raoult's law. So as we all know that a solution is made up of two components. So one is solute, another one is solvent. Solute, anything which is present in a smaller quantity, and solvent is something which is present in larger quantity. So if I take the example of salt in water, salt plus water, or sugar in water, so we can easily say that water is the solvent and the salt and sugar, this is solute. Okay, so when anything which is present in large quantity is solvent, fine. But what if I say 44 gram water and 54 gram we have salt, any salt, you can take it as NaCl. So if the amount is same, so because we are defining it on the basis of amount, so if amount is same, then how can we predict which one is solute, which one is solvent? So first of all, we generally take water as a universal solvent. So of course water is going to be the solvent, but there comes a relation of mass to mole ratio. So if we calculate moles of these two, so first if I calculate moles of water, so I can write number of moles of water is given mass of water, that is 54, divided by molar mass, so it will come out to be 3. Similarly, if I calculate number of moles of NaCl, so it will be given mass by molar mass. Molar mass of NaCl is 58.5, so it will be somewhere less than that less than 1, so it would be somewhere around 0.9, or if I write it very precisely, it would be 0.92, that is same thing. So 0.92 moles, whereas water it has 3 moles. So of course anything which has greater moles, so again water will be the solvent based on number of moles. So if amount is same, we can predict it on the basis of number of moles. Okay, then there are different types of solutions that we know. One is solid in liquid, like I discussed, salt in water, sugar in water, then liquid in liquid, ethanol in water, or anything. You can say H2SO4 in water. Then gases in liquid, lot of gases, oxygen, nitrogen, they dissolve in water. So that becomes a gas and liquid type solution. So these are the various types of combinations of solution which are possible. So if the solvent is gas, so we call it as gaseous solution. If solvent is liquid, we call it as liquid solutions. If it is solid, then we call it as solid solutions. These we have discussed. It is also in grade 9th chapter, solution suspension and colloids. So this we already discussed, molality, mole fraction, and this relation from molality to mole fraction is very important for competitive exams. Mass percentage, similarly we have volume percentage, then parts per million, parts per billion. This already discussed in part 1. So today we will discuss about Henry law and Raoult's law. So if I begin with Henry law first, so the very first thing that comes is solubility. What is solubility? So the definition says it is the maximum amount of solute that can be dissolved in 100 gram of solvent at a specific temperature. Suppose right now temperature is 40 degrees Celsius. So the amount of anything which can be dissolved uh, into a 100 gram of solvent, that defines the solubility of the solid into the liquid. So that defines the solubility of the solvent. So if I take solvent as water, then that will be the solubility of water at this temperature. So solubility of solid into liquid, it depends upon various factors like nature of solute, nature of solvent, and temperature. So if I talk about nature of solute, so a rule that applies everywhere is like dissolves like dissolves like. That means if the solute is polar, then solvent must be polar, and vice versa. If it is non-polar, then solvent must be non-polar. So like dissolves like. Polar is dissolved in polar solvents, and non-polar compound is dissolved in non-polar solvent. Second is again nature of solvent, the same thing, like dissolves like. It if the solvent is polar, then solute should also be non-polar, polar only. So again, third part is temperature. So generally, I'm saying generally, this is not applicable everywhere because we have two exceptions, lithium sulfate and sodium sulfate. So except few exceptions, temperature varies directly with solubility of solids, solubility of solid in liquid, with some exceptions like lithium sulfate and sodium sulfate, because they vary irreversibly. There is a case of transition temperature. First is increases, then it decreases in sodium sulfate, but lithium sulfate, it is inversely proportional to the temperature because these are exothermic. Then energetics, that means what energy changes are involved in dissolution process. So there are various types of energy: solute-solute interaction, then we have solvent-solvent interaction, then solute-solvent interaction. So I will be representing solute as B. So B interactions, then solvent as AA interactions, then solute-solvent interaction as AB interaction. So these three type of interactions are possible. Suppose AB interaction means solute-solvent interaction is greater than AA or BB, means solute solvent interact strongly, then this is the best condition for solubility. So these types of gases or solids, they get dissolved easily because after combination A and B, they are more, uh, there is a more interaction. So this is the most favorable condition. Then after this also works sometimes if AB is less than AA or BB, then it also works, means by increasing temperature, these types of solids can be dissolved. But third condition is if AB interaction is much smaller than AA or BB. That means AB interaction is very less in comparison to the interaction between solvent-solvent and solute-solute. Then in this case we write no dissolution, means there is no solubility. Why? Because AB interactions are very weak in comparison to solute-solute and solvent-solvent. Then another reason for solubility is ion dipole interaction. So how these ion dipole get generated? Suppose I take the example of sodium chloride. So Na is plus, water molecule is like this, water, then H, then H. So because of negativity, oxygen is having a negative charge and hydrogen is having positive charge. So this is a sort of dipole. On one side we have this positive electron density, on the another side we have negative charge. So this generates a sort of dipole. So since Na is plus, so you can see this is the structure. So Na is plus, so negative end of oxygen, this is the end of oxygen. So negative end of oxygen is tilted towards positive charge. So all these are oxygen atom with negative charge. So these are pointed towards sodium. Whereas chlorine is negatively charged. So now you can say these two hydrogens are pointed. So now oxygen is moving away because like charges repel. So now hydrogen, these positively charged hydrogens, these are pointing towards this negatively charged chlorine. So this type of process is called hydration. Hydration. Common name for this one is solvation. Solvation is the effect of solvent. So when water is the solvent, it is called hydration. So hydration is basically, circling and circling of any ion by water molecule. This is called hydration. There are various types of energies involved. So suppose any lattice, this sodium chloride lattice is formed. So for that we represent it as delta H of L, means delta H enthalpy of lattice formation. Similarly, this lattice for hydration is represented as delta H H. So when we add these two energies, so it is the sum of total energy, that is delta H of solvation. So this is the equation which is important for competitive exams. So what is solvation energy? It is basically, sorry, this would be S here and H here. So solvation energy is the sum of hydration energy plus lattice energy. So ion dipole interaction, they also play a very crucial role in solubility. Now, just like I discussed, so factors which affect solubility is nature of solute, in which like dissolves like. That means polar dissolves in polar and non-polar is soluble in non-polar. So if I take example of polar in polar, so water is polar, ethanol is polar. So C2H5O, they get solubilized because both of them are polar each like. Similarly, if I take example of non-polar, so benzene is non-polar. Similarly, I have C6H5, then CS3. This becomes toluene like this. So these two again are non-polar, so they are soluble in each other. They are miscible liquids. Second, if we discuss about solubility of solid, so solubility of solid, it generally increases with temperature, except this sodium sulfate and lithium sulfate. These two are exceptions because the dissolution of sodium sulfate and this lithium sulfate is exothermic in nature. So any process which is exothermic, if you increase temperature for a process which is exo, so according to Lee-Chatelier principle, any process which is exothermic, if you are increasing temperature, so what will happen? A reaction will go in backward direction. So that is why for these two, sodium sulfate and lithium sulfate, the temperature plays a opposite role. It means solubility does not increases. Second, for solubility of gases, this part is very important. Solubility of gases, it decreases with increase in temperature. So why it decreases? So just imagine if I take oxygen, suppose oxygen gas is there, and this is a river. So oxygen, when it is in air, so entropy high entropy. Why? Because in gases, if oxygen is present in gaseous state, randomness is going to be high. So high entropy, the moment it dissolves in water, so now it is in liquid state. So in this case, here for oxygen, entropy decreases. It is quite evident. Anything which comes from gaseous state to liquid state, so it proceeds by decrease in entropy. And we all know that the equation from uh, thermodynamics class 11th, that delta G is equals to delta H minus T delta S. So in this case, means dissolution of oxygen in water is accompanied by decrease in entropy. That means delta S is what? Delta S is negative. So if this delta S is negative, so this negative and this negative, it becomes positive. That means delta H plus T delta S. So again, dissolution of oxygen is a spontaneous process because oxygen is dissolved in seas and oceans. No one is going and mixing this oxygen. It is occurring spontaneously. That means this process is spontaneous. So if this process is spontaneous, that means delta G must be negative. But from this equation, we have this value positive and this is also positive. So this part can become negative only when delta G is negative. So that is why when delta H is negative, we say the process is exothermic. So even if you don't know the back end story, just remember that dissolution of gases, dissolution of gases is exothermic. So if dissolution of gases is exothermic and you are increasing temperatures, that is why with increase in temperature this decreases. Why? Because again Lee-Chatelier's principle. Lee-Chatelier's principle. Why? Because resolution is exothermic, and when for any process which is exothermic you increase temperature, so reaction goes backward. That is why solubility decreases. And I tell my students in grade 12, we all have come across this poem, that is मछली जल की रानी है, मछली जल की रानी है. So I generally make a correction, मछली जल की रानी है, but मछली ठंडे जल की रानी, because when you increase temperature, the solubility of oxygen decreases. So these aquatic animals are not comfortable, they die. That is why the temperature of the water must be low. If it is low, then only solubility of oxygen is high. Fine. So now coming to this part, Henry law, which is very important. So Henry law talks about the solubility of gas in liquid. So it gives a quantitative effect of pressure, means what is the effect of pressure on solubility of gas. And this law states that the solubility of a gas, the solubility of a gas in a liquid is directly proportional to the pressure of the gas. That means if I write it in mathematical form, I can write it as solubility is represented as zeta, so mole fraction. So it is proportional to the pressure. So even I can write it in other way. So P is proportional to mole fraction. So if I remove this sign of proportionality, so what I can write is P KH psi B, and this KH is nothing but this Henry constant. KH is called Henry constant. Now what important conclusion we can derive from here is, so if I write the same expression in another way, so I can write this expression in form of KH. So KH will be I can write it as 1 by chi B of gas, or you can simply write it even chi also, into P. P is pressure. Pressure is some quantity, 1, 2, 3, 110 atm, whatever it is. So again, it is some constant. So when I remove this proportionality constant, so I can write KH. If I remove this pressure constant, so I can write it like this, chi V. This conclusion is very important. That means chi is what? Mole fraction, and mole fraction is what? Solubility. So you can write very important conclusion that solubility is inversely proportional to Henry constant. That means if Henry constant increases, then solubility decreases. So this conclusion becomes very important for multiple choice question. So you have three different gases A, B, C. For them, KH value is given. For this, it is 50. For this, it is 60. For this, it is 70. So unit of KH is same, just like pressure. We will come to that. Suppose it is, ATM, and then it is also ATM and ATM. So KH values are given. So the question that is asked is, out of these three gases A, B, C, which one is having highest solubility? So since A is having lowest value of KH, so A will have the highest solubility. Lower the value of KH, higher is the solubility, and vice versa. Okay. Second thing that we can write from this part is, we know that from this equation, I should remove this one. So we know that pressure is equals to Kh into mole fraction. Even in previous lecture, I told you mole fraction is the only concentration term which has no unit. It is unitless. Molarity is mole per liter, molality is mole per kg. Everything is having some unit, but mole fraction is unitless. So if this quantity is unitless, that means whatever is the unit of pressure, that will be the unit of Kh. So you can write unit of Kh, units of Kh. So it is same as pressure. So I can write the units of pressure as torque or bar or even mmHg or like that. All other units, like we have mm of Hg, then we have ATM also, Pascal also. A lot of units are there for pressure. So it will be same. Whatever is the unit of P, that will be the unit of Kh. That's it. So this is Henry law. Solubility of gas in liquid is directly proportional to the pressure of the gas. This is Henry law. Now there are few limitations of Henry law, that is, pressure of the gas is not too high and temperature is not too low. The This is very important. Gas should not undergo any chemical reaction, any chemical change with the solvent. Third part, the gas should not undergo association or dissociation. That means if it is oxygen, so it should be molecular oxygen only. It should not become anything else, like, you know in atomic form, or after combination with O, it should not become O3. That means there should be no chemical change, which should neither undergo association or dissociation. There are various applications of Henry law to increase the solubility of CO2 in soda water and soft drinks. The bottle is sealed at high pressure. So whatever we have, Coke, or nowadays we have Campa. So the moment you open that uh, bottle, so you get a lot of fizz. This fizz is only when temperature is low. That means you take that bottle out of refrigerator. Then only you observe this fizz. Suppose that soft drink is hot. It is at 40 degrees Celsius. Means it is not in refrigeration. So if you open that bottle, because of high temperature, that CO2 is not dissolved. So that is why the moment you open that bottle, CO2, it leaks to the atmosphere, and you get very, very, very small or even no fizz, because solubility of carbon dioxide is not there at high temperature. And that is why it tastes, it flat, no taste is there, because CO2 is not there. And to avoid the toxic effects of high concentration of nitrogen in the blood, so generally these scuba divers, they mix that uh, cylinder of oxygen with helium in order to avoid bends. So why do they mix this oxygen with helium and nitrogen? Because it has, low solubility. So in order to avoid bends, it is scuba divers, they dilute that air with helium and nitrogen. Third application is at high altitude. Low blood oxygen causes climbers to become weak and make them unable to think early, which are symptoms of conditions known as anoxia. So these are few applications of Henry law. Okay, so this question is very important if we talk about Henry law. So in even in board exam, this question comes every 3 or 4 years, after every 3 or 4 years. So H2S is a toxic gas with rotten egg-like smell. It is used for qualitative analysis. So not to forget, this is H2S is used in salt analysis. Salt analysis that is a part of experiment in group 1, group 2, and so on. This is used in qualitative analysis. So if solubility of H2S in water at STP is 0.195. So the moment we see this 0.195, 0.195 molal, it is written small m, molal. So molal, what is the definition of molal? Two things we can derive from this. Molal means number of moles of solute present in per kilogram of the solvent. So 0.195 molal means 0.195 moles, 0.195 moles of H2S are are present in 1 kg. 1 kg means 1000 gram of solvent. So this is the information that we get from 0.195 molar solution. Now, 1000 gram of solvent. So since no solvent is mentioned, so I will take water as a universal solvent. So calculate number of moles of water, number of moles of water. Now, what is the amount of solvent? So from the definition of molar, we get to know that it is 1000 gram in 1000 gram, 1000 gram. So even we did this yesterday in first part. So 1000 divided by molar mass of water. So this value is very, famous one, 55.55 moles. So these are the number of moles of water present in 1 liter. And this is number of mole of water. Okay. Number of mole of H2S already given, 0.195. So from this we can calculate mole fraction of H2S. Mole fraction of H2S is what? Number of moles of H2S divided by number of mole of H2S plus number of moles of water. So from here we can write number of moles of H2S are 0.195, 0.195 divided by 0.195 plus 55.55. So when you solve this, we get 0.195 divided by 55 point 55 points. So if you sum this 0.195, it becomes 5 4 7 745. So when you solve this one, this number 0.195 divided by 55.745, so we get this value as 0.0035. This is the mole fraction of H2S. So now we know that according to Henry law, according to Henry law, according to Henry law, we know that pressure of H2S is what? It is Kh into mole fraction. Mole fraction means X. This we have calculated. It is 0.0035. So in this case, now what is the value of pressure? So it is written STP, standard temperature and pressure. Standard pressure is 0. Either you can take it, if you take it as ATM, it will be 1 ATM, or if you take it as bar, it will be 0.987 bar, because it is written STP. So from standard pressure, I am writing this value. You can also take 1 ATM, then answer will be in ATM. I am writing it as bar, so answer will be in bar. Kh into 0.0035. So now when you calculate KH, it comes out to be 0.987 divided by 0.0035. So this answer is, I think, very common one. 282 bar is the correct answer. 282 bar is the correct answer for this question. Okay. Okay, so it is solved also. So you can refer to this solution 282 bar. So it is means if it is not mentioned, then you can take here 1 ATM also. So calculation will be very easy. So if you write it as 1 ATM is equals to KH into, so you can directly divide it by 0.0035. So whatever answer you will have, that will be in ATM. Either you can report it in bar or ATM. Okay. Again, this question is very important from Henry Law. These two questions, I think only these two questions are there in text. So the both of them are important. So Henry Law constant for CO2 in water is this one. Henry Law constant means KH is given. This one, add to 98 Kelvin. Calculate the quantity of CO2 in 500 ml. Now see here it is not 1 liter, it is 500 ml. That means amount of water is going to be 500 ml, not 1000. When water is packed at 2.5 atm CO2. So very first thing what you can see is 1 unit of pressure is atm, another unit of pressure is Pascal. So either convert this Pascal into atm or atm into Pascal. So what I can write, pressure of CO2 is, it is written pressure of CO2, quantity of CO2 soda water when packed in 2.5 atm. So it is written 2.5 atm. So I will convert it into Pascal. So 2.1 atm is equals to, although it is I think 1.0135 something, but I'm roughly taking it as 1 atm is equals to 10 to the power 5 Pascal directly. So you can also use it, but the actual value is somewhere 1.013 into 10 to the power something. So 2.5 atm, I will directly convert it into Pascal. So 2.5 into 10 to the power 5 Pascal. So now we know that according to Henry law, we can calculate this is P is equals to KH into chi mole fraction. So if I have to calculate mole fraction, then I can write P divided by KH. So what is pressure? We just calculated P. It is 2.5 into 10 to the power 5. What is the value of KH? It is already given. Henry law constant for CO2 in water is this. So KH is given 1.67 into 10 to the power 8. So this 10 to the power 8, it goes up, it will be minus 8. So I can write mole fraction is equals to, so it will come out to be, if you solve this one, it will come out to be 1.52 into 10 to the power minus 3. So I'm assuming it to be equation A, because this is important. It will help us later on. Okay, so this is the mole fraction of CO2 that we have calculated from this data. From the second part, we can also calculate mole fraction of CO2. So mole fraction of CO2 can be written as mole fraction, because I need to calculate number of moles of CO2. So mole fraction of CO2 is equals to number of moles of CO2 divided by number of moles of CO2 plus number of moles of solvent. So solvent is water. So I can write number of moles of CO2 is equal, sorry, mole fraction of CO2 is equals to number of moles of CO2. So this I have to calculate, because we know the formula. Ultimately, what we need to calculate the quantity of CO2. This is the question. So to calculate quantity of CO2, what is the formula of number of mole? Number of mole is equals to given mass by molar mass. Molar mass of CO2 is 44. That means given mass can be calculated if I multiply number of mole by 44. So that is why I am calculating number of moles. So number of moles of CO2 divided by number of moles of CO2 is also here. So one thing that approximation we have to do in this case, see, mole fraction of CO2, it is 1.52 into 10 to the power 3. So if I write it in absolute number, mole fraction is somewhere around 0.00152. So that means mole fraction is very small. So this part, number of mole of CO2, we will eliminate, or we can ignore this value because mole fraction of CO2 is very small. So we can ignore number of moles of CO2 in denominator. So I will only write number of moles of water. Here you can also mention, since mole fraction of CO2 is very small, so we are ignoring the number of moles in denominator. So number of moles of CO2, it will be number of moles of CO2, number of moles of water. Now, how can we calculate number of moles of water? It is, either if you are taking it as 55.55, that is for 1 kg of solvent. Here it is written 500 ml. So for water density is 1, so 500 ml becomes 500 gram also. So when you divide this number 55.55, so either you can take 55.55 and whatever results come later on divided by 2, or simply, since volume is 500 ml, so we can directly write 55.55 divided by 2, so it will come out to be 27.775 in 500 ml. So 27.775 is nothing but number of mole of water. You should not have any confusion. 500 gram by 80. So if you divide this, this will come out to be 27.775. Mole fraction of CO2, we have already calculated this value. So when I write this equation again, so I can write it as number of moles of CO2 is equals to mole fraction of CO2 into 27 point this. So what is the mole fraction of CO2? 1.52 into 10 to the power minus 3 into this value 27.775. So if you multiply this number, so it will come out to be 0. So I should multiply this number. So if I multiply this number 1.52 into 27.775, so it will come out to be, I'm writing it as 42.218 into 10 to the power minus 3. Okay, so these are the number of moles of water. So how can we calculate mass of CO2? So mass of CO2 will be number of moles of CO2 into its molar mass. Molar mass is 44. So when you multiply this 42.218 into 10 to the power minus 3 into 44. So what value we get is, it will come out to be 1.86 grams. So this is the answer for this question. So what you need to know first, step by step. First, make the units of pressure as same. So either you can convert Pascal into ATM or ATM into Pascal. So I have converted this ATM into Pascal. So once these two units are in Pascal, both of them, then you can calculate KH, Henry constant. When we know this value of KH and this value of pressure is also in Pascal, then we can calculate mole fraction. The moment you get mole fraction, so using this formula of mole fraction, we have to calculate number of moles of CO2. Again, second most important part is this value. Number of moles of water, if it is instead of 500, if it is 1000, then you will take it as 55.55. But since it is 500 ml, so you will take it as half of 55.55, which is 27.77. And then solve this, and ultimately you will get the number of moles. Then multiply number of moles with molecular mass, then you will get the actual mass. So answer is 1.86. This question is very important for board exam. So that was coming to be 1.86. In this solution it is 1.83, some approximately it is same. So using this you can also calculate. So again, listen, this it is written 500 ml and density of water is taken as 1. So 500 ml becomes 500 grams. Okay. So these two questions are very important from this part. Now moving to the second part of this today's quiz is vapor pressure of solution, which will lead us towards uh, Raoult's law. So vapor pressure, as the name suggests, it is the pressure of vapors. So vapor pressure of a liquid is defined as pressure exerted by vapors above the liquid surface in equilibrium with the liquid phase. So just imagine these two beakers. So these are covered with some glass. So in this case, we have pure solvent. Pure solvent. Solvent is, solvent is volatile. Volatile. So volatile means all these, these particles of solvent are volatile. So all of them are in equilibrium with the liquid phase. There is equilibrium between vapor phase and liquid phase. Now, if I add little amount of solute which is non-volatile. Non-volatile means it does not evaporate. So if it is not evaporating, so that means some part of the per surface like this green balls, this one. So some part of the upper layer is occupied by solute particles which are non-volatile. That means suppose if you assume 100 particles are there in both the cases, 100 here, 100 here, in both the cases. So in if it is pure solvent, then all these 100 100 particles are converting into vapor phase. But since in this case when we add non-volatile solute, so even if I take it as 50-50, so 50 are volatile of solvent, 50 are non-volatile of solute. Now uh, it is very clear that only four these particles are there, whereas there are so many in this case. That means when we add any non-volatile solute, the rate of evaporation decreases. So here so many particles are there in this case, whereas these particles are less. This is called you know dec decrease in vapor pressure. So why there is a depression in vapor pressure or decrease in vapor pressure? Because we are adding non-volatile solute, non-volatile which does not evaporate. They remain at the surface, hence there is a decrease in or depression in uh, vapor pressure. So this is called lowering of vapor pressure. In terms of NCERT, it is lowering of vapor pressure. Now reason for lowering of vapor pressure, it is, I think it is clear to everyone, because we are adding non-volatile solute which are non-evaporating in nature. So they remain in the surface, hence vapor pressure decreases. So vapor pressure of liquid is depend upon the following factors. First, nature of the liquid. So liquids having weak intermolecular forces are volatile. So it is quite obvious. That means if there is a force of attraction between two particles is less. So if it is less, that means even a small amount of energy can break this bond. So that is why they become highly volatile. So liquids having weak intermolecular forces are volatile and therefore have high vapor pressure. Second factor is temperature. So as we all know, as we increase temperature, evaporation, rate of evaporation increases. So as the rate of evaporation increases, So vapor pressure, number of number of particles in vapor phase will increase, and therefore vapor pressure will also increase. This is because you know high kinetic energy of the molecules. So they have high kinetic energy, so they form more number of particles are there in vapor phase. So they have higher tendency to escape from the surface, and they have high tendency to be in vapor phase. Okay, so now coming to the Raoult law part. So first we will discuss part A, vapor pressure of solution of solids and liquids. So when any solid is dissolved in liquid. So it states that the vapor pressure of a solution containing a non-volatile solute is directly proportional to the mole fraction of the solvent. So this is the statement of Raoult's law. That means vapor pressure of the solution containing non-volatile solute is directly proportional to the mole fraction of the solvent. Now you don't need to memorize it. You can simply just try to understand it. When we represent solute is represented by V, solvent is represented by letter A. So when we are adding non-volatile solute, that means these are not going to evaporate. So that means solute has no role in vapor pressure. So vapor pressure is only because of solvent, because solvent is only component which is volatile. So as we increase more and more solute, more and more non-volatile component, that means vapor pressure will decrease. Okay, so it will decrease the mole fraction of the solvent. Okay, so I can represent this form, this definition, like vapor pressure of a solution. I can write it as vapor pressure of a solution. I can write it as is equals to vapor pressure of solvent in solution. I can write it. There should be no confusion. Why? Because vapor pressure of solution is equals to vapor pressure of solvent in solution. Why? Because solute is non-volatile. It is not going to evaporate. So there are no vapors from solute. So hence no vapor pressure. So it is inversely proportional to what? Mole fraction of the solvent. Mole fraction of the solvent. Why? Because solvent is the only component which is uh, playing a role in vapor pressure. So as we increase mole fraction is what? Quantity of solvent. So more quantity of solvent, more is the vapor pressure. So there should be no confusion. That means what we can write is vapor pressure. I am representing it as P, vapor pressure, and that too of A, that means it is of solvent. So it is what? Directly proportional to the mole fraction of the solvent. This is what I have written, uh, vapor pressure of the solution, which is nothing but the vapor pressure of the solvent is directly proportional to the mole fraction of the solvent. So I can write it PA is directly proportional to mole fraction of A. Now if I remove this constant of proportionality, I can write PA is equals to some constant K into mole fraction A. Okay. Now, if I take this is very important for a pure liquid. For a pure liquid, suppose there is no, no solute. It is only pure liquid. So if it is pure liquid, that means only pure solvent. So for that, mole fraction of solvent will be 1, because mole fraction of all component is 1. And if there is only one component, so mole fraction of this will be 1. So in this case, when this chi A or zeta A is 1, so put this value into this one, then what we will get? PA is equals to K, because chi A is 1. That means K is what? K is another constant which is nothing but vapor pressure of the pure solvent. So the moment I put not, that means it is for pure liquid. So hence K is what? P naught. So equation this you can take it as A this equation as B, then I can write the third and final equation, which is PA is equals to P naught A, zeta A or chi A. This is the statement of mathematical expression of Raoult law. So even, you can write it that vapor pressure of, vapor pressure of solution is equals to vapor pressure of pure solvent into mole fraction of solvent. So this is just the expanded version of this equation. So this equation tells us about the first statement of Raoult's law, which states that the vapor pressure of a non-volatile solute is directly proportional to the this one vapor pressure of a solution is directly proportional to the mole fraction of the solvent. Okay. Then second part, this part is most important, I would say, because from here we get a colligative property also, relative lowering of vapor pressure. So what is relative lowering? So if I write mole fraction, if mole fraction of solute is, since I'm representing solute as B, so mole fraction of solute is XB or chi B, and we know that mole fraction of all component is equals to 1. That means I can write chi A is equals to 1 minus chi B. There should be no confusion. So in the previous slide, look at this one, this equation, and in this case, this is another equation. Chi A is what? 1 minus chi B. So from these two equations, since we just derived it, PA is equals to P naught A chi A, and chi A is what? 1 minus chi B. So I can write it as P naught A. At the place of chi A, I can write 1 minus chi B. So if I rearrange it, I can write it as PA is equals to, multiply this one. So this will be P naught A minus P naught A chi B. So again, if I rearrange it, so I can write it as P naught A. So if it goes this side, so this will be P naught A minus PA, and if this minus P naught, this goes to this side, so it will be positive. So this is equals to P naught A chi B. So if I write the final statement, chi B, what is that? Is mole fraction of the solute. So it is nothing but, put a bracket here, so this will be P naught A minus PA divided by P naught A. This is another statement of Raoult's law. This is another statement of Raoult's law. So this part, P naught A minus PA. This is, P naught is what? Pure vapor pressure. This is vapor pressure of solution. That means this is pure and this is of solution. Solution means we have added non-volatile solute into it. So after that, PA is the result. This is of pure. That is why it is called lowering of vapor pressure. So this is the vapor pressure which gets lower when we add non-volatile solute, and this is lowering of vapor pressure. And if I divide lowering of vapor pressure P naught A minus PA, if I divide this quantity by P naught A, this expression, this one, this becomes relative lowering of vapor pressure, because now we are relating this, uh, you know, lowering with a reference. The reference is what? P naught A, pure vapor pressure. So this becomes relative lowering of vapor pressure. So this quantity P naught A in this part, P naught A minus PA divided by P naught A, this is called a relative lowering of vapor pressure. Hence, we have this alternate statement of Raoult law. What we can write? This part is relative lowering of vapor pressure. Hence, alternate statement of Raoult law is for a solution containing non-volatile solute, relative lowering of vapor pressure is equals to the mole fraction of the solute. This part, mole fraction, chi b of the solute. And hence we have another definition or another mathematical expression for Raoult law. So this is again very important. You should be very clear with lowering of vapor pressure and relative lowering of vapor pressure. Okay. Now, this is I would take another example, means another type of, you know, okay, fine. So if I have to write the another statement of Raoult law for binary solution, Raoult's law for binary solution. Binary means having two liquids into it. So if I write for first one, this is what? PA is equals to P naught A chi A, and for second solution I can write PB is equals to P naught B chi B, because these two are from that Raoult's law definition, where P naught A and P naught B are the pure, vapor pressure of pure components, pure A and pure B. Okay, so from here we can write, if I write from the Dalton's law of partial pressure, we know that total pressure, P is what? Sum of both the pressures PA and PB. So when I sum these two pressures, I can write PA is what? P naught A, P naught A chi A, PB is what? P naught B chi B. Again, we know that we have one, formula chi A plus chi B is 1. So we can write, you can put any value. So I can write this any part, suppose chi A as what? 1 minus chi B. So I will be replacing this chi A with this number. So I can write P naught A, at the place of this I can write 1 minus chi B plus P naught B xB. So now multiply this number, so it becomes P naught A minus P naught A xB plus P naught B xB. So now take xB as common. So if I take this xB as common from this part, xB both. So if I take xB as common, so what I have is P naught B minus P naught A plus P naught A, this P naught A. So this expression is again very important. This is P. So one form can be derived by replacing chi A as 1 minus chi B. Another form can be derived by replacing chi B as 1 minus chi A. So if I put this chi B in the same equation, then another equation that I will have is P is equals to, with respect to chi A, then it will be P naught A minus P naught B plus P naught B. These two formulas are very important for, to solve any numerical. Okay, so again, if I plot, remember these two equations. So if I plot the curve, so if I write this in form of y is equals to m x plus c, y is equals to mx plus c. So if I plot a curve between these two at y-axis, if I write p, m is the slope. On x-axis I have, so wait, this is y is equals to, this is the slope m and this is x. So on this axis I will have xb, and this is the slope HIB. So then we get, if I plot it one more axis from this side, then so if chi b is increasing towards this side, that means at this point chi b will be maximum, and at this point chi b will be 0. Similarly, chi a is maximum on this side, and 0 is on this side, and highest one, because mole fraction can be maximum, it can be maximum as 1. So chi b is decreasing towards this, increasing towards right side, and chi is increasing towards this side. So if I plot this curve, so what I will get is something like this. This is the line for these two. So if you add these two, so this line represents total pressure. P is equals to PA plus PB. Now compare y is equals to y on this side, x on chi b on this side, and this is m, intercept. So sorry, this is the slope P naught B minus P naught A. What is the intercept? P naught A. So at this moment I will have this part is, so look at this one, A is highest on this side. So if A is touching this axis, this is P naught A, and B is highest on this axis towards right. This maximum point represents P naught B. So these are the two intercepts from these two equations. All right. So that's what is represented in this graph. So when you put it as any, you can take any equation from this one. So I'm taking it as y is equals to, this is the slope m, this is x plus c. So y is equals to mx plus c. This is the intercept P naught A. So you can see this is the intercept for one equation, and similarly for second equation that I have written, you will get second intercept, which is P naught B. So this is all about Raoult's law for both uh, for solid and liquid and for binary solutions. So both of these two equations, this equation and first part along with relative lowering of vapor pressure, these two are very important. So I think in the previous slide I forgot to mention from this part also, if I have this equation, where is that equation, k into xa or p naught into xa, you can take any equation. So this is the equation for Raoult's law. Okay, fine, this is the equation for Raoult's law. So I can plot the similar, same type of curve here also. So where I have this ways to plot this curve. So again, you can take it in a similar way. So equation that I have is P is equals to PA is equals to P naught A chi A. So again, if you write it in form of y is equals to x m, here we have nothing, so plus 0. So plus c is what? 0. That means no intercept. So if I write one axis on this side, so y axis it is PA. So I'm writing on y axis PA. X axis I have chi A. So chi A is on x axis. This is origin. So what is the intercept? 0. Intersect 0, that means the graph must, this line must pass through origin. And wherever it is, reaching this chi A is increasing towards that. So I'm assuming this point as the maximum mole fraction for A component. So this part, highest part of this one will be P naught A. So this is your, you know, intercept that it is making. This is related loading of air pressure, Raoult's law. Okay, so this again, this I think this question has not been asked in CBSE last couple of years. So this part becomes very important for this year, 2027, I would say. Means composition in vapor phase. So whenever two volatile liquids are mixed, so there exist vapors which is in equilibrium with the liquid surface. So composition of vapor phase, we can also calculate the mole fraction or composition of vapors. Composition of vapor phase in equilibrium with the solution can be calculated from partial pressure of the two components of the solution. So this part is represented as YA and YB. Suppose YA and YB, these two represent the vapor phases of components A and B. Then these composition can be calculated as YA is equals to mole fraction of A into pure vapor pressure of A divided by total pressure. Similarly, vapor pressure means vapor phase composition of B is equals to mole fraction of B, pure vapor pressure of B divided by total pressure. One question I have picked up from NCERT only. So the vapor pressure of pure A and B is 450 and 700. That means these are the values. This value is P naught A and this value is P naught B, pure vapor pressure. Find composition of liquid. Total vapor pressure PT is also given. So we have to calculate this composition. What we have, we know PA, we know PT, we know P naught B, we know PT. We have to calculate basically chi A and chi B. That means mole fraction of A and B. So how can we calculate? So right now we have derived this equation. Total pressure PT is what? It is the sum of PA plus PB. So PA and PB is what? P naught A chi A plus P naught B chi B. Again, I will do the same thing. So either replace chi A or replace chi B. So this time I can replace chi B. So this will be P naught A x A plus P naught B. At the place of x B, what I can write? 1 minus x A, because sum of both the component is always 1. So now PT, we know what is PT. PT is, it is written 600 mmHg. So 600 is equals to P naught A is also given. It is 450, this value, and PA chi A. So this XA we had to calculate, so I'm writing it as it is, plus P naught B is also given. It is 700. So 700, 1 minus chi A. So 1 minus chi A. I have written it as it is. So if I solve this equation, so I can write 450 XA plus 700 minus 700 XA. So 450 XA minus 700 XA. So this becomes minus 200 XA. So what I can write it as 600 is equals to 700, this number 700 minus 250 XA. So from here I can calculate XA. This XA will come out to be 0.4. So if it is 0.4, so sum of mole fraction of all component is always 1. So there are two components. So if it is 0.6, so chi B will be 0. If it is 0.4, this will be 0.6, because sum should always be 1. So chi A is 0.4, chi B is 0.6. Now we can calculate this YA and YB. So I am calculating YA. YA is what? So chi A is 0.4 into P naught A. P naught A is 450 divided by total pressure. Total pressure is 600, or it is 600. In the question, it is written 600. So this will be 600. So when you solve this, it will come out to be 0. Or I should solve it. So this will be 0 0.56, 0 0.3. This will be divided by 600. So it will come out to be 0 0.3. This is 0 0.3. So if this is 0 0.3, then you can also calculate YB is equals to chi B. This we have calculated 0 0.6 into P naught B. P naught B is 7. P naught B is 700. P naught B is 700 divided by total pressure. So the total is again 600. So this value YB will come out to be, if you solve this, it will be come out to be 0 0.7. So this is 0 0.7. This is 0 0.3. So this is, in this way we can calculate vapor phase composition. Okay, one conclusion you can also derive from here is, chi A we have calculated this value. Chi A is 0.4, XB is 0.6. That means this composition of A is 40%. This is 60%. So 40-60. But see here in vapor phase, it is not 40-60. It is 30-70. So which vapor pressure is increasing? This has increased from 60 to 70. That means this question, even I can add one more part. So if you have to find which component is more volatile, so you can see from 40-60 it is becoming 30-70. In vapor it is becoming 70. So you can write B is more volatile. Why? Because it has higher composition in vapor phase. So this can also be asked, or you can also add from your side. Okay, so based on Raoult law we have different types of solutions: ideal solution, non-ideal solution, then its types, positive, negative, deviation. So ideal solution, anything which is ideal, either ideal gas or ideal solution or ideal student or ideal teacher. So anything which is ideal, it has to obey all these rules and regulations. So ideal solutions are those solutions which obey Raoult law. That's it. Ideal student is that student which obeys, all the rules, regulations of a school. Similarly, ideal gases are those gases which obeys the, laws of uh, gaseous states. So similarly, these solutions. Now these interactions, just like I defined in the first or second slide, three types of interactions are there. AA, that means between solvent solvent, BB, solute solute, AB, solute and solvent. That means these three interactions are of same magnitude. This part is very important. So since all these are of same magnitude, that is why they are called ideal solution. They do not deviate from their ideal path. So there are various examples. Benzene plus toluene, because benzene is this one and toluene is this. So both of them are almost similar structure. Hexane, heptane. So hexane is having, 6 carbons. Heptane is having 7 carbons. So again, almost same structure. So although it is cyclohexane, cycloheptane, but ethyl bromide, ethyl iodide. So C2H5Br and C2H5I. So since all of them are almost similar, identical not identical, but similar in nature, so they are, examples of ideal solutions. This is most important. Delta H mixing and delta V mixing is 0 for ideal solution. That means when two ideal solutions are mixed, so there is no, change in enthalpy and no change in volume, no change in enthalpy, because they are ideal. Although this is not in NCERT, but Delta G mixing, Gibbs free energy of mixing is always negative and entropy of mixing is always positive. You can add these 2 points. The Gibbs free energy always negative and this entropy change is always positive. Then ideal solutions, so we have non-ideal solutions also. Those solutions which do not obey Raoult's law. So again, these are defined in two ways: positive deviation and negative deviation. Positive deviation means this is the expected line. This is the expected vapor pressure which is calculated using Raoult law, and this is the actual one. That means actual one is little bit higher than calculated. So if it is higher, so that means vapor pressure is high. Vapor pressure is high, that means particles are in vapor phase more. So more vapor phase, that means interactions are less. So that is why these type of positive deviations are formed when AB interaction is less than AA or BB. That means after mixing the interactions decreases. That is why more vapors are formed. More vapor, that means more vapor pressure. More vapor pressure, that is why from it is higher than calculated. Similarly, for negative deviation, so this is the expected line based on the calculation of Raoult law. But this is the expected, this is the actual line. So that means actual solution is having less vapor pressure than calculated. So why it is having less vapor pressure? Because the moment we mix these types of you know solvents, so they are after mixing the interaction increases. So now after mixing either they are undergoing some changes. So after mixing, AB interaction becomes higher than AA or BB. That means in solvent itself, in solute itself, these interactions are low, but the moment solute and solvent is mixed, this interaction is high. So now if solute and solvent are mixing, that means they are becoming more stable. So more stable, that means they have less tendency to vaporize. So less tendency to vaporize, that means vapor pressure is decreasing. That is why we are getting lower vapor pressure as calculated or as expected from Raoult's law. So in this case, both of them are higher. So that is why we are having delta H positive, delta V positive, because volume also increases because of no interaction or less interaction between AB. Here delta H is negative because process is exothermic, because after combination these AB is getting stabilized, and anything which when it gets stabilized it releases energy. So this process is exo. That is why delta H is negative. Delta V is also negative. Volume slightly decreases because of more interaction between AB. So more interaction, closer packing, dense packing. Again delta G mixing is negative, delta S mixing positive, delta G mixing negative, delta S mixing positive. It is same. These two components are same. Either it is ideal or non-ideal. It is same everywhere. So now you can see for positive deviation, that means where AB is less than AA or BB. So where solute solvent interaction is less. So you can see acetone, ethanol, because ethanol is having hydrogen bonding. So ethanol itself is very happy alone, but the moment you mix it with acetone, so hydrogen bonding gets disturbed. So because disturbance in hydrogen bonding, so now these interactions are lost. So both of them then have tendency to evaporate. So it causes more vapor pressure. Similarly, acetone is having it is having carbonyl carbon, so it is happy with itself. But the moment you mix carbon disulfide CH2, so it is non-polar. So it decreases the this interaction between acetone molecules. So again, it destabilizes this acetone. Again, we have CCl4, carbon tetrachloride, and chloroform. Chloroform is CHCl3. So we have, CHCl, Cl3. So because of 3 chlorine atom, this is having positive charge. Carbon is having a positive center. So that is why this positive center is interacting with another chloroform molecule. But the moment carbon tetrachloride is again non-polar, CCl4, CCl4, it is having no interaction. So it is no interaction, it is also disturbing the interaction of chloroform. So it disturbs chloroform, hence both of them, tend to vaporize. So more vapor pressure. So the same thing follows in the other examples. But these negative deviations are different. Why? Because after mixing, their strength increases. So AA is less stable, solute is less stable, solvent is less stable. But solute solvent, they form, good company. So chloroform, it is having 3 chlorine methyl acetate. So the moment it gets, COCS3, COOCS3. So again, a type of ion, again it is having chloroform, positive center. So ion-ion interaction. Acetic acid, then pyridine. Pyridine is this one. Pyridine, it is having lone pair. So it is, basic in nature, available for protonation. Acetic acid is H plus. So it easily protonates this one. So these two are complementary. So that is why interaction increases. Acetone and chloroform, very good combination. Why? Because, chloroform is this one. Chloroform is CH, chloroform is this one, CHCl3, and acetone is this one, CO CS3. So this center is, negative because of, sorry, this center is positive because of 3 chlorine atom, and this oxygen is having high electron density, itself having lone pair and being electronegative, it attracts electrons. So these electrons and this positive center, positive and negative center, they are, they tend to have higher interaction. Similarly, water and sulfuric acid. So this, what you have to remember or understand is, in this case, AB is less than AA, VB. In this case, AB is greater than AA or VB. That's it. So these two are the categories of uh, positive and negative deviation from Raoult's law. Okay, then comes another concept that is called constant boiling mixtures. Another name for them is azeotropes. Azeotropes. Azeotropes are constant boiling mixture. Constant boiling mixtures. That means these are the mixtures which boil at the same temperature, and even they have same composition in vapor phase. So they have same composition in vapor phase also. That is why it becomes, very difficult to separate them, because they, you know they convert into vapor state at the same temperature. So it becomes very, very difficult to separate them, and that these are called azeotropes. So azeotropes are, again, two types of azeotropes are there: minimum boiling azeotrope, maximum boiling azeotropes. So if I have to define it, I will define it. First, minimum boiling azeotrope. Minimum boiling azeotropes, as the name suggests, they require minimum boiling. So they are formed by, positive deviation. Positive deviation, that means in which interaction of AB is less. So positive deviation combinations, they form minimum boiling azeotrope. Like we have H2O plus H2, H2O plus H2SO4. So there is, although you don't need to remember it, 5% of H2O and 95% of H2SO4. So boiling point of H2O is 100 degrees Celsius, For H2SO4, it is somewhere, I think, 351 Kelvin. It is 373 Kelvin. So this is having higher boiling point. But when it is mixed, so water also boils at 351 Kelvin. That means it decreases from 373 to 351. That is why it is called minimum boiling azeotrope. Another category is maximum boiling azeotropes. So they are formed by negative deviation. Negative deviation means which have better interactions. So AB is having better interaction than AA and BB. So like again, I can take one example of HCl and water. So HCl and water. So again, we know that water boils at 373 Kelvin, 100 degrees Celsius, and boiling point HCl is actually a gas. So its boiling point is 188 Kelvin. So, but when we mix approximately 20% this and 80% water, 80% water. So even this HCl, its boiling point also increases from 188, and this both of this entire mixture, it boils at 383 Kelvin. So can you imagine this? Even water degree of this boiling point increases by 10 degree or 10 Kelvin. So this is called maximum boiling. That means these types of combination, because after mixing they form good bonding or good interaction, so their boiling point increases. So that means you have to boil them to a maximum, even greater extent. So that is why they are called maximum boiling azeotrope and minimum boiling azeotrope. So that's it for today. In the next class, probably we will discuss about colligative properties. So these are the examples that I have discussed: minimum boiling azeotrope and maximum boiling azeotrope. These are the example, and these are the percentage. Although you don't need to remember it, this is just to just to have some examples, so just to feel it. Okay, so in the next class we will discuss colligative properties.